Quicksort is fast and efficient, and unlike some of the other algorithms that we've covered on this channel, it's actually used in the real world. Looking at you, BubbleSort. Quicksort is a divide and conquer algorithm, just like mergesort. And while it technically has the same big O complexity as mergesort, order n log n, it doesn't require so much memory, and it doesn't have to copy elements from sublist to sublist. It actually sorts the entire list in place, which means that it can be more performant. All right, let's dive into how it works. We'll start with a random list of numbers. The first thing we need for Quicksort is a pivot number, and to keep things simple, we'll just arbitrarily use the element at the end of the list. In this case, 5. Next, we need 2 pointers, I and j, to keep track of things as we're gonna be swapping them around. I will start at the first number, 8, and j will start at the second number, 3. Now at each step, we're going to compare j to the pivot. We're not comparing j to I, that does confuse some people. J to the pivot. So in this case, we'll be comparing 3 and 5. And because 3 is less than 5, j is less than the pivot, we're going to swap I and j. We'll also move the I pointer forward. Now I understand that it's a bit funky. We're comparing j and the pivot, but actually swapping I and j. Just remember that. All right, and now we just do it again. So now we'll compare j to the pivot again, in this case, 2 and 5. And again, because j is less than the pivot, we're going to swap I and j and move I forward. Next, we compare 9 and 5. Now this time, j is greater than the pivot. So no swaps. We move j forward, but we do not move I forward. 1 is less than 5, time to swap I and j again, and we'll increment both pointers. 7 is greater than 5, so no swaps here. 6 is also greater than 5, again, no swaps. 10 is greater than 5, no swapping. 4 is less than 5, one last swap. Now, if you take a look at the list, all of the numbers before I are smaller than the pivot, and all of the numbers greater than I are larger than the pivot. So that means if we swap the pivot with I now, it will be in its perfectly sorted place, with everything less than it before it, and everything greater than it coming after it. Now, that's just one round of the partition function in Quicksort, but frankly, it's the interesting part. The way we turn this partition function into a full-blown Quicksort is by recursively calling this partition function. So we'll continuously partition, do this algorithm, over and over on each half of the list until the full list is sorted. Now, remember how I mentioned that Quicksort is generally more performant than mergesort? That's true, but it does have a dark side. If we consistently pick the smallest or largest element from the list as the pivot, it gets really slow and will actually degenerate into order n squared in big O terms, which effectively makes it a bubble sort equivalent, which is something that no sorting algorithm wants to be. But honestly, that shouldn't scare you. There's pretty trivial ways to make sure that Quicksort never degrades. For example, we can just check and make sure that the list isn't pre-sorted. We could randomize the list before sorting it, or we could even pick the pivot at random for maximum chaos. Anyways, optimized versions of Quicksort are used all over the place in the real world. Most languages' standard libraries actually do use Quicksort, at least for part of the standard implementation of their sorting algorithms. Now, so you can properly visualize it end to end, here's a full animation of Quicksort on a larger data set. And here's another full animation, but where the list is already sorted and the performance degrades. You'll notice that it's a lot slower.